of the same material we just heard about, the 316
Right.
Right?
Thank you. Yeah, good morning, ladies and gentlemen. I'm Awanish Mishra, and I'm from Indian Institute of Technology at Ropar. I'm working as a research scholar, and my paper 029. I'm an author, and my co-authors Avinash Gopalan and Amnani Babu, B. Karthik. These are from Indira Gandhi Admission Research Center, India, and Mr. Ritesh from MNIT Jaipur, and Dr. Abhishek Tiwari, my supervisor, is from IIT Ropar. So, my topic is creep crack growth characterization of SS316. So many talks here is on creep, and this is my talk on creep crack growth. This is the area of fracture mechanics. So welcome you all. The story is starting from the heat transfer system of the phosphate reactors. Basically, in India, the development of reactors in a different three phases. The first phase, they are developing the pressurized heavy water reactors, where the natural uranium is used as a fuel, and after that, they are new reactors, that is pressurized heavy water reactors, but the fuel is man-made fuel, uranium. But India have a lot of thorium sources. For utilizing that thorium source, they are developing the fast-feed reactors. So fast-feed reactors have a main component like reactor vessels, intermediate heat exchangers, and the primary sodium circuit and the secondary sodium circuit. So you see here in the pictures very clear that the temperature variation is from 380 degrees Celsius to 550 degrees Celsius. And in the transient condition, some NE pumps are failure. At that time, it reaches up to the 650 degrees Celsius. So here is the requirement to select the best suitable material which have a capability to show the better strength, better creep strength at 650 temperature. And these are the area where the using the structural material like structural components. These are main vessel, core support, sodium pumps, safety vessels. These are the area where the requirement of the structural material. So for these all consideration, India is using for the reactor vessel, intermediate heat exchanger, primary sodium circuit pipe, and the secondary sodium circuit pipe. There the working condition, that is 400 to 650 degrees Celsius, and very low pressure. They are using the SS316 LN. So in a previous talk, we're talking about the SS316 LN. So what the India is using the SS316 LN, the carbon percentage is 0.027, and the nitrogen percentage is about 0.7. So here is playing with the problems with the sensitization. Actually, in a normal SS316L, it's reduced by introducing the nitrogen. So nitrogen, basically what it's do, it's just by increasing the nitrogen, stacking fault energy decreases, and stack size increases, and very difficult to cross slip. So it helps to strengthen the material at a high temperature. So the things is the life prediction is important. So creep crack growth is a technique. How it is important, why it is important? Because suppose that the material is operating at a high temperature, so there is a chances for the diffusion domination, vacancy is created, micro cracks are there, and it leads to the cavities and cracks present in the system. Sometimes this type of the cracks is coming into the manufacturing defects also. So if any component have a crack and its working condition is the time dependent plastic deformation, there is the creep condition. So the creep crack growth study is very, very important for that condition. Okay, so if a creep deformation in a structural material, So how we characterize the crack? The problem, we all know about the linear elastic fracture mechanics and elastoplastic fracture mechanics. These are basically not valid when the condition is creep. The time dependent deformation is here. So we cannot use these parameters like LEFM and EPFM parameters. We cannot use. So we have only the parameter, this is the dynamic time dependent deformation. So the time dependent deformation parameters, dynamic parameters are used for characterizing the crack in these conditions. So other parameters have been worked out, and depending on the magnitude of creep zone in the materials. So for this, what are the different creep zones and how we apply the different parameters to characterize the crack in these conditions. So we try to understand what is the different regimes for the creep and how it is characterized. Suppose that when initially loaded the material, so initially the very small creep zones are formed at an crack tip, and this size is very less compared to the ligament length. This is called a small scale creep. And if the creep zone size is just covered up all over the ligament length, this is called extensive creep condition. And if the creep zone size is in between the small scale creep and extensive creep, this is called a transition creep condition. But the problem is this, how we characterize and how to find out the stress and strain in the creeping condition at a crack tip. So for the small scale creep, basically the problem with this, for the characterization of these two parameters, like a small scale creep and a transition condition, we cannot use the normal parameter like a C star, because with the help of C star we can only characterize the extensive creep condition. So Riddle and Rice is basically proposing this equation for the CT integral, which is used for the initially for it's famous for some time, and after that there is a problem because this is dependent on the creep exponents values, and it cannot be found out experimentally. So theoretically we can find out with the help of this expression, and after that Saxena is giving this expression for find out the to characterize the small scale creep and the transition creep by experimental calculation. So this expression used for this, and here is one thing. What is the C star and how it's come into the picture, and what are the analogy with the J integral? So I hope most of you is aware with the J integral, and this nothing which this is given by the J Rice by considering the concept of deformation theory of plasticity, where only the loading is allowed, no unloading is there. So for assuming this condition, this is deformation theory of plasticity, and this comes by Rhombus-Woodward relation expression. This is N is the strain hardening exponent, and when this condition is valid, then we can apply the J integral. And here phi is the strain is density. We can find out with the help of stress strain graph. Okay, but the things is a steady state power law when the creep is there, and the things is just a time dependent deformation. So here is a strain rate. This is given by Hoff's analogy. It's told that the strain rate is the function of stress. When this condition is valid, then we can apply the C star. But this condition is failed here in the case of small scale creep. You see, this is the strain rate is the function of stress rate. That's why we cannot apply the C star here. So the C star is just similar like J is path independent, and similarly C is also the path independent. And the real problem is this. When the crack, suppose that when the crack is growing like this, so the condition, the consideration is taken by Rice is failed. Basically, here is unloading. When the crack is continuously growing, so just behind the crack tip, there is unloading. So this concept of J Rice is like this. when you are applying the load, it's follow the same path. Loading and unloading is in the same path. But in the case of incremental theory of plasticity, it does not follow the same path. In the deformation theory of plasticity, have a one stress, have a one strain value. But incremental theory of plasticity is not valid. For one stress, have a two strain value. So this incremental theory of plasticity is if the real scenario condition, physical condition, with the help of that we can validate the real scenario, which is going on in the when the crack is growing. So for this concept, these are the open questions to you all. Is application of C parameter is physically sound? And the C star and the CT is basically give the driving force, and how to quantify the driving force of a keeping material SS3 versus L. So basically C star and CTs are not able to tell anything about the driving forces. J is only tell about the energy release rate. C star is tell nothing like that. So these parameters, the line integral, they is used for only find out the stress and strain on the crack tip during a creep condition. But the things how to solve these problems. So for the solving these problems, the new concept which is used by Koladnik in the area of the fracture mechanics recently. So this is the configurational forces. So the concept of configurational forces is not very tough, it's very easy, and this is the driving force. When the suppose that this is the interstitial atoms and it sit on the octahedral or tetrahedral wax, and the surrounding atoms are bigger, they are producing some compression here, but the some another atoms is on the surface which have a lesser compression because the free surface is there. So due to this there is an energy difference, and due to the energy difference there is a movement if the path is available. So this driving, so the driving means the due to the potential difference of the energy, here is the driving forces, and this is called a configuration forces. So by using this concept in the field of fracture mechanics, the bulk configuration forces, with the help of this expression, I have to use this concept to apply find out the configuration forces where the material is creeping. So C is a stress tensor, whereas phi is the energy density, I is the identity vector, F is a deformation gradient, and S is the first final pressure tensor. So the divergence of anything will give, this is the tensor just converted into the vector, and the negative sign shows that how much energy goes in the system and how much energy goes out from the system. And suppose the singularity at an crack tip, so we can say that the configuration forces are 0 in this condition. So how we find out the configuration forces? Basically we are taking the configurational forces around all the sample, and we are projecting in the particular direction. By taking the projection in desired crack growth direction, we find out the crack growth driving force in the particular direction. So these are my results, and before discuss about results, I just tell something about how I perform my test. So I have used the ASTM E standard 1457, and as per ASTM standard, I have made the sample first. CT sample I use for this test, compact tension test. Use at a temperature, I use the 650 degrees Celsius temperature, and at a 650 degrees Celsius I have tested different load, 10 kN, 12 kN, 14 kN and the 16 kN, and for the maintaining the temperature use the K-type thermocouples, and for monitoring the crack growths use the DCP. So these are the experimental procedures I use for the characterization, and basically a creep crack growth with first I plot with creep crack growth with normalized time. I found that with increasing the load, the deformation time and the creep crack growth is decreasing, because of the wire manipulations for high load is less, it's take the less time to deform and to nucleate at a grain boundary. So, but the things is that the main parameter, that is a C star. So for defining the C star, we basically the things very important, that is load line displacement. So in the case of creep, that is the load line displacement rate. So load line displacement rate is the combination of elastic load line displacement rate, plastic load line displacement rate, plus creep load line displacement. So standard ASTM E81457 told that you take the total load line displacement rate, because the creep domination extensive creep is there. So we use the use the total load line displacement rate, and I have to change something. I just reduce the plastic effect and the elastic effect, and I want to see what are the any plastic effects is on a creep or not. So for this I perform and analyze this result. Then I found that the all the unfilled boxes, it show the normal C star versus dA by dt. So for the initially for 10 kN as 12 kN and the 14 and the 16 kN. So 12 k in the 10 kN, there is a this results initially there is a lower crack growth we observed, because this is initially the stress relaxation is there. So due to the stress relaxation, it compresses the void formation, and then we see that continuously by increasing the load, C star value increases because it's depend on the LLD, total load line displacement rate. So by increasing the load line displacement increases, and due to this the C star values increases with the load value. And after that the JP I consider, it means plasticity. What are the effects of plasticity? So I don't found any effect on the plasticity for this material, because creep is there. So I don't found any more effect on the plasticity on this material. So it shows that there is extensive creep, and creep domination is very high. So for the validation of this thing, for this concept, whether I am wrong or whether I am right, I have done some simulation work. So for ensure my result, I have performed the simulation work, and I have done the node release technique. And with the help of node release technique, I just simulate the experimental results with dA by dt, and with different steps I form, and by different step I perform the test and find out the plastic zone size and the creep zone size. So it shows that here the creep zone size is very highly dominated, and the plastic zone size is very less. This is consistent. So this analytical results is that expression is given by Ashok Saxena. So theoretical creep zone size is in between this, and its result shows that the domination of creep zone size on the for this material. Okay, and after that, by the post processing, actually we have a in-house programming for this, and Python coding and some C programmings. For this, I have to find out the configurational forces. So basically, the configurational forces are distributed all over the sample, and this is used to find out in the desired crack growth direction. So by taking the projection of all the forces in desired direction, like FEPC, this is the forces distribution within the material, and we find out the JEP by taking the projection of this FEPC in a desired crack growth direction. So here is the results. I find out the CT very near to the tip, like a 4 mm, and CT away from the crack tip. So it shows that here in this result, it shows that there is a similar CT4 and the CT5. These values are showing the same trend. It shows that the CT is path independent. But the configurational force result dJEP by dt for the different control value like a 4 mm, 6 mm, 8 mm, 10 mm and 22 mm, these are basically path dependent. So this is dJEP by dt very near to the crack tip,